Today we are very happy to have Rose Kudzman-Blais from the University of Kyoto, who will talk about bicategorical semantics for non-commutative linear logic.
Okay, so hi everyone. Like Zainab said, I'm now at the University of Kyoto. My name is Rose Kudzman-Blais, and I'll be talking about the categorical and bicategorical semantics for non-commutative linear logic. And this presentation sort of came about after my thesis, where I was considering semantics, bicategorical semantics for non-commutative linear logic, but focusing on not having negation present. And then now that I'm here, I'm really am thinking more about how negation can be present. And what I've realized is that there's many different alternative ways to just, define that. So this presentation is going through all of these alternative ways. So it will be very definition heavy, but that's sort of the point, is showing how all these definitions really do come out to represent the same thing. And hopefully, while you might not remember all the definitions, you get the idea of how they all are one and the same. So we'll be starting off by giving you sort of overview on linear logic and most importantly, multiplicative linear logic, because that's really the only thing we'll be looking at today. We'll start with the commutative version that you might be more familiar with, and then look at non-commutative linear logic. There's many variants. We'll be concentrating on cyclic linear logic and bilinear logic as the relevant variants. Then we'll look at the categorical semantics for that, and then bicategorical semantics for those two. So linear logic, well, Girard introduced it as a substructural logic without contraction weakening in 1987. And like I said, we're primarily concerned with the fragment known as multiplicative linear logic. So we're not considering the additive connectives nor the exponential connectives, pardon, although these can be added into the story. Although a lot of that stuff for the bicategorical hasn't really been done yet. So that's open for further research. So the important connectives and constants for MLL, multiplicative linear logic, are your multiplicative conjunction and disjunction, where conjunction is known as tensor and you have the normal tensor symbol, and then disjunction is known as par, where you have this upside down ampersand. And then we have linear negation and linear implication, which is that lollipop symbol for implication. And here's the sequent calculus for MLL. We won't really go through it, but what I want to call your attention to is this exchange rule that tells you, that you can rearrange your formulas via any permutation, and that's allowed. And this is the rule that makes it a commutative logic, okay? And that's the rule that will be changing in the variants that are non-commutative. So here are some basic properties about our multiplicatives in MLL. So if you have two formulas A and B, well, first things first, linear negation is involutive. So A perp, which perp means this linear negation symbol, gives you back A. Also, your multiplicative constants are related by what we call a De Morgan duality. So the multiplicative constant for conjunction, right, this one, perp is the same thing as bottom, the multiplicative constant for disjunction, and then vice versa. Also, any multiplicative binary connective you can define in terms of any other one with linear negation. So there's a lot of formulas here. The most important I want to call attention to is the first one, which we call this De Morgan duality as well. So A tensor B is equal to A perp par B perp perp, okay? And another important thing to call your attention to is how you can define linear implication in terms of linear negation and tensor. So A implies B, which I'm using the word implies for this lollipop symbol, is the same thing as A tensor B perp perp. So those are the most important ones I want to call your attention to. Also importantly, is the one on the bottom right hand, A implies B is also definable as A perp par B. And that's really just from the fact that, A tensor B is definable in terms of perp. So Okay. And what we can actually prove from the above is that linear implication has to satisfy the following. A perp has to be A implies bottom. So you can define linear implication, sorry, you can define linear negation in terms of implication and bottom. And so what this tells us, what I really want to draw your attention to, is that if you have tensor or par, you can define linear implication using linear negation. And then if you additionally have this constant bottom, then you can define linear negation in terms of linear implication. Okay? Now, the categorical semantics for MLL were investigated by Seely in 1989, who showed that they were given by star autonomous categories, which were previously introduced by Barr. So a star autonomous category, in this sense, as a symmetric monoidal category X with a tensor product and a unit, with a full and full functor star from X op to X, such that we have this natural isomorphism. So all our maps from A tensor B to C star, are in isomorphism with our maps A to B tensor C star. Now, this should perhaps not be familiar to everyone, but star autonomous category are, a categorical structure that's used a lot. Now, you can prove that a star autonomous category is closed, right? Is symmetric monoidal closed by defining the internal HOM as follows. Now, you should recognize that this is precisely one of the formulas we had on the previous page. This is linear implication in terms of tensor and linear negation. Moreover, you can, given a star autonomous category, you can define a par structure as follows. And this is once again precisely the formulas we had on the previous page. And this will give you a valid symmetric monoidal category. And it's in this way that a star autonomous category really models all those connectives and constants we had, right? We get multiplicative conjunction from the tensor product, negation from this star, implication via the closure structure defined as follows, and then the par via this construction here. All right. But there's many alternative definitions for star autonomous categories. The most important one is the following, okay? And this was, given by Barr. So a star autonomous category is a symmetric closed monoidal category. So you're asking for closure. And you need a dualizing object bottom, which is an object such that this canonical map is an isomorphism for all A. What that map is just currying with closure the evaluation map. Now, why does this work? Well, essentially, you're just following what we talked about in MLL, right? If you have linear negation, your star, you define your closure, as we discussed previously, and you define your dualizing object as the De Morgan dual of your monoidal unit. If you have a dualizing object and closure, linear implication, then you just define negation as we had on that previous slide, right? And so this asking for this object to be dualizing, for this canonical map to be an isomorphism, is just asking for A to be isomorphic to A perp. So you're just forcing this A implies bottom to really be an involutive operation, like linear negation. Okay, so here, what I want to call attention to is your first definition uses negation to define implication and your bottom constant, I guess, while the second uses implication and the constant bottom to define negation. And that's really sort of the guiding thread throughout this entire presentation. In every instance, we're going to have these equivalent definitions where you define either the negation or the implication and bottom. Okay? So some quick examples. Girard's category of coherent spaces and linear maps is star autonomous, okay? And the dualizing object is the singleton coherent space. That's sort of the example Seely gives to show that star autonomy really is the right thing, because Girard gave two semantics for his linear logic when he introduced it, the one of them being the coherent spaces. So it's important that it works. Another important example is your category of superlattices and superserving maps, and then your dualizing object is just the true 0, 1 superlattice op, because your linear negation is just opping stuff. Now, every compact closed category is star autonomous, with the monoidal unit being the dualizing object. And in fact, you can sort of say that uh, compact closed categories are star autonomous categories that satisfy an additional um, sort of coherence between linear negation and tensor product, right? This one particularly, that it commutes. And then there's the famous true construction, whereby you take any symmetric monoidal closed category with pullbacks and you consider a distinguished object, and you essentially build the category such that that distinguished object is forcibly, the dualizing object, right? And I've given the construction here and all the necessary references. Okay. Well, in his original article, like I mentioned, Girard provided two semantics for linear logic: coherent spaces and phase spaces. Now, phase spaces already hinted that non-commutative linear logic should be a possible further direction, because he kind of forces the commutativity to be there, and it's sort of completely natural to not have it have been commutative. He even says it in the article, but Yetter takes that on in 1990 and looks at this non-commutative variant that he calls cyclic linear logic. And again, we'll be interested in the multiplicative fragment that I'm calling multiplicative cyclic linear logic, pardon, MCLL. And it's exactly the same sequent calculus. The only thing is you replace the exchange rule by a cycling rule, where you only allow specific cyclic permutations, right? You don't allow all permutations of formulas, only cyclic permutations. Why? Well, this is essentially forced if you want to have one notion of linear negation, okay? So you don't ask for your conjunction and disjunction to be commutative, but for there to only be one version of negation, you need to allow cyclic permutations. And so because conjunction and disjunction, aren't commutative, you have two versions of implication. We're going to call the right lollipop right linear implication, and then left lollipop left linear implication. So here are some basic properties again in MCLL. Linear negation remains involutive. You get your multiplicative constants one from the other by De Morgan duality. And then you can get any binary connective from any other via linear negation. The only thing here is you have to be careful about how you write your formulas, because disjunction and conjunction and your implications are no longer commutative. So what you want to notice is that A tensor B is in fact B perp R A perp perp, right? That was different from the commutative version. You could have written that for the commutative version because it didn't matter, but in this instance, you have to be quite careful. So it's the same stuff, just careful about in what order you're writing your formulas. And then right and left linear implications satisfy the following. So A perp is equal to A implies bottom, but it's also equal to bottom left implies A. So in fact, while implication left and right linear implication aren't equal, they are for the specific situation where you're, got bottom. And you can prove that using the previous formulas there. Okay, so that's cyclic linear logic. What if we drop the cycling rule entirely? Then you necessarily get two notions of linear negation. And this variant of non-commutative multiplicative linear logic, which is essentially just removing the exchange rule entirely, was studied by various different authors around the same time and given different names. So actually in 1958, Lambek introduced a substructural deductive system he called syntactic calculus, because it had applications in linguistics. And that was sort of a fragment of what comes to be bilinear logic. And he unified his syntactic calculus with linear logic in 1993, noticing, the fact that it was already sort of a fragment. And he called that bilinear logic. And it was in fact borrowing from work earlier by this Russian author Grishin, whose original article is in Russian, actually, so I haven't read it myself. But Lambek cites it, and yeah. But around the same time, in 1991, Abruzzi developed what he called non-commutative linear propositional logic to look at, okay, removing the exchange rule with a focus on phase spaces, removing the cyclic part of Yetter's phase spaces. And this is all the same thing, essentially, bilinear logic and what Abruzzi did. And so I think nowadays it's called, more commonly called bilinear logic. So that's what we'll call it. And again, we're looking at multiplicative fragment of it. And that's essentially multiplicative linear logic without your exchange rules, leading to two notions of linear implication and linear negation. I won't give you the secant calculus because it's a little bit more involved, but just note here that we're going to call when we do perp on the right, right linear negation. When we do perp on the left, we get left linear implication. All right, so here again, let's talk about some basic properties. Linear negation is involutive, but this time you need to be careful. If you're left linear negating, then you're right linear negating to get back to A, and vice versa, okay? Because again, you've got two versions of linear negation. Your multiplicative constants are related by De Morgan duality, and here you see that left and right linear negation are the same on the constants, essentially. Again, you can get any binary connective defined of any other using both right and left linear negation. And it's the same formulas. You just have to be careful about using the right and left in the appropriate ways. So A tensor B is left negation of B right negation par A right negation, or dually right negation of B left negation par A left negation. And so it's the same thing for A and right implies B and B left implies A. You just need to be careful about where your left and right linear implication, or sorry, negation are in the formulas. And what you get is that right and left linear implication satisfies the following. A right perp is A right implies bottom, and A left perp is bottom left implies A. If I get lost a little bit in saying this out loud, sorry, it's a lot of words, but the formulas are on the slides. But those aren't equal, right? This was equal in the cyclic case. They're not equal in this case. And another thing I want to call your attention to, which is the part that, where Grishin's work had come into play, you have these Grishin laws that hold that you can fairly easily prove based on what the formulas I gave above. But you have that A right implies B, par C is going to be equal to A right implies B, par C, and then dually for left implication. These will come up in our semantics. So I just wanted to call attention that they hold. All right, so let's talk about the categorical semantics for both bilinear logic and cyclic linear logic. So in 1995, Barr extended star autonomous categories to the non-commutative setting to get multiplicative bilinear logic. And so a non-symmetric star autonomous category is just a monoidal category with this equivalence functor star from X to X op such that we have this natural isomorphism. Now, since it's an equivalence, there's a hidden functor there, which is left star. And that the fact that it's an equivalence tells us, in fact, that left star applied to A right star is isomorphic to A, and then A left star right star, right? And so that secondary left star is our other form of linear negation, not hiding, but within the definition. And so you can reformulate it a little bit so it looks maybe a bit more like your standard version of star autonomy, right? And basically you can say that you have an equivalence from X to X ops such that you have these natural isomorphisms, which are precisely the sort of the same ones we had in the star autonomous normal case. You're just being careful about one, writing your tensor like in the right order, because A tensor B is not the same thing as B tensor A. And you're being careful about which star you're using, right? You have to use sort of both. But it's the sort of same natural isomorphisms. One thing to note is that given this formulation, the right star models left linear negation and the left star models right linear negation. So ideally, we would change the notation, but I wanted to give it in Barr's sort of way of presenting it in case people wanted to go back and look at his article. But yeah, that's a bit unfortunate. Okay, so a non-symmetric star autonomous category is biclose, and you define your internal hums precisely the way I was giving them in that previous slide from bilinear logic, right? A right implies B is left star of B star right star tensor A. And then, dually. Again, remembering that left star is right negation and right star is left negation. So as you would expect, you can redefine this in terms of linear implication, right? So you can say that a non-symmetric star autonomous category is a biclosed monoidal category. Oh, did I have that written twice? With a dualizing object. What's a dualizing object? It's an object bottom such that these two canonical maps are isomorphisms. And we have two of them this time because, we're non-commutative, we're non-symmetric. You have two versions of implication. You have right closure and left closure. So the first one's obtained by left currying the right evaluation map, and then the second one's obtained by right currying this left co-evaluation map. And really what these are saying is if we're defining A implies A implies right implies bottom to be right negation, and dually, this is saying that A is isomorphic to A right negation, left negation, right? So it's just involutive being careful about the two versions of negation. So we get the Barr structure as follows. You define it, via the De Morgan dualities, being careful about right versus left. And this is a valid, monoidal category. But the thing about this is Barr is really sort of extra structure here, right? It's not you sort of define it separately. And so can you consider semantics where you're putting conjunction and disjunction on a level playing field? Well, that's what Cockett and Seely were thinking when they introduced this alternative semantics for multiplicative linear logic, which actually, works with and without negation, in 1992, when they brought linearly distributive categories. The thought process being you want conjunction and disjunction to be primitive, right? Tensor and Barr. And this really provides a model for a minimal logic, right? Which is essentially non-commutative multiplicative linear logic without linear negation and linear implication. You just got two connectives, two constants, introduction rules, and Gensen's cut rule. And it promotes the importance of distributivity between tensor and Barr, which had previously been sort of under researched. So what's a linearly distributive category? Well, a linearly distributive category or an LDC is a category with a tensor monoidal structure, a Barr monoidal structure, and then these left and right linear distributivity natural transformations. So A Barr B tensor C gives us A Barr B tensor C. So tensor sort of binds more strongly. And this is precisely what you need as categorical semantics to model the cut rule without, linear negation there. And so they provide, this categorical semantics for this minimal type of logic. Notational conflict. Cockett and Seely change some symbols. I'm going to stick with Girard's notation for this talk, but I usually use Cockett and Seely's notation. So if there's any, mistakes later on, just let me know because I might have, missed one. All right. Examples, every monoidal category is an LDC. You just take tensor and Barr to be the same thing. Then your linear distributivities are just associators. And we call these degenerate, but they give us a whole host of examples. Every star autonomous category, standard or non-symmetric, is an LDC. That's important, right? If we were really taking a fragment of MLL, the full MLL of star autonomy should definitely be an LDC. And it's now a standard exercise to show what the linear distributivities are in the star autonomous case, how you get them from negation. Another source of examples are these shifted tensors, or the categorical analog of shifted monoids. Because of time, I won't go through this though. So we're particularly interested in having negation, right? So in order to model multiplicative bilinear logic and recover non-symmetric star autonomy, you want linear negation in the context of LDCs. How do you do that? You look at complementation pairs. So given an LDC, you say that a complementation pair, a complement, gamma and tau, is this object A, the left complement, AC, the right complement, and this pair of maps from A tensor AC to bottom and 1 to AC par A. And you want to satisfy these following diagrams, which are essentially linearly distributive snake equations. Okay, and that will be made a little bit more precise. But if you have a complementation pair, then you in fact get these adjunctions. So A tensor blank is left adjoint to AC par blank. And if you look back at what we had, you essentially see that AC acts as the right linear negation of A, and dually A acts as the right linear negation of AC. So having linear negation is essentially being an LDC, which has a coherent way of associating a left and right linear negation, so a sort of left and right complementation pair. And that's made explicit here. So an LDC with negation is one that has object functions right perp and left perp, and these parametrized families, such that a perp gives you a complementation pair, and then a left perp A is another complementation pair. Okay, so these complementation pairs precisely give us linear negation. All right. Well, what about defining linear implication, or sorry, linear negation in terms of linear implication in bottom, which in this case, we have bottom already. It's baked into the structure of LDCs. It's the linear implication part that we need to worry about. And this was given by Grisham LDCs, which they're called Grisham because of the these Grisham laws. So a Grisham LDC is an LDC whose tensor monoidal structure is closed. So we get linear implication right and left. And then you want these following canonical maps to be isomorphisms. And these maps are obtained as follows. So you use linear distributivity and then your evaluation maps. And these are, precisely the Grisham laws. Okay. And they essentially allow for defining it when we're going to go from one to the other, defining these complementation pairs to be the proper complementation pairs. They force A right implies bottom to be, the complementation of A. But we need these Grisham laws essentially. So if we put all of this work together, we get the categorical semantics for multiplicative bilinear logic. You've got non-symmetric star autonomous categories defined in terms of linear negation with your stars. You have them defined in terms of implication and bottom. You get linearly distributive categories with negation and these Grisham linearly distributive categories. They're all the same thing, and they all provide categorical semantics for MBLL. And the proof is fairly simple. It's all given by those formulas from MBLL, right? You just have to show that it follows, it satisfies all our categorical properties. But it's the same formula as I originally gave, just being careful, again, that right star is left linear negation, just because of the way it's defined. Okay. Now let's talk about some examples. I would say perhaps to me, the most important example of a non-symmetric star autonomous category is the poseidal category of relations on a specific set. Your monoidal product is just your standard relational composition. Your dualizing object is the inequality relation. And then your linear negation is taking the complement inverse. So R perp is all the x prime such that x prime x is not in R. So you take the complement and you op it. You take the transpose of the relation. Note here that R right perp and R left perp are the same. Abrupsky, when defining MBLL, essentially, he talked about non-commutative classical phase spaces. So he took the phase spaces from Girard and made them non-commutative. And then the two construction was extended to be non-symmetric by Barr. And it's a much more involved construction because instead of just giving, so the two construction essentially you take an object and you pair it with what should be its linear negation. But since A right perp isn't A, you have to associate with that A many, many, many. So it's not just a pair. So it's a much more involved construction, but it works, of course. But what we see here, especially with the first example, which this is really, you can do this for anything profunctor-like. Okay, I'm just using rel because it's straightforward and simple to explain, but there's so many variants to this idea here with profunctors. But they really only have one version of linear negation, right? So it makes sense to look at the cyclic linear logic version because a lot of these more natural, quote unquote, examples really do have one version of linear negation. So, like I said, in 1990, Yetter introduced cyclic linear logic and gave quantile semantics to capture it and to look at non-commutative phase spaces, not in the sense of Abruzzi. There's a cyclicity here that Abruzzi considers without the cyclicity. But then the general categorical semantics were given by Rosenthal in 1994. And they're kind of what you expect. So you start with a biclosed monoidal category, right? Okay. And we want it to be dualizing. So at this point, we've got a non-symmetric star autonomous category in the way Barr had defined it previously. What do we need to make it cyclic? We want linear negation to only be, to only have one version. You want A implies right, so A right implies bottom, and bottom left implies A to be isomorphic to one another. And that's precisely what you ask. You say that the object is cyclic if you have this isomorphism satisfying that coherence diagram there, okay? And this is precisely what Yetter had said, just in terms of quantiles, right? And then Rosenthal just made this in terms of categories. And then so you say, okay, that the categorical semantics for cyclic multiplicative linear logic is a biclosed monoidal category with a cyclic dualizing object. I've written the same thing twice here, but I'll fix that in the slides that I upload. Now, the definition of cyclic star autonomous categories in terms of linear negation and its linearly distributive variance, right? Because remember the non-symmetric star autonomous case, we had 4 variants of the same thing. These don't exist or in the literature yet, but it should be very straightforward given that these variants do exist when we go to the bicategorical way. So should be straightforward to write down, although they don't appear in print yet, unless I'm mistaken and someone has a reference. So here are some examples. Rel, right? Rel on one set X is a cyclic star autonomous category. Okay, Yetter's non-commutative phase spaces are cyclic star autonomous category. You ask for this bottom essentially be cyclic. That's the difference with Abruzzi's. And then Barr considered the true construction for non-symmetric biclosed monoidal categories, but assuming your distinguished object is cyclic in some ways. And that's a much more straightforward construction, actually, because your two versions of linear negation are the same. Okay, so let's look at bicategorical semantics now. Well, to model non-commutative logical connectives, what we've been doing so far is looking at non-symmetric monoidal products, which is fine. But in some sense, the most natural perspective is to look at bicategorical composition, right? Because non-symmetric monoidal products are just bicategorical composition on one object. And composition is an intrinsically non-commutative operation. Just look at, personally, my favorite example of a non-symmetric star autonomous category, it's relations on X. We're looking at our conjunction as a form of composition. What if we want to make X non-fixed? Then we're looking at bicategories. And it's with that mindset that Cockett, Kowslowski, and Seely looked at linear bicategories and cyclic star autonomous bicategories in 2000-2001 to look at bicategorical semantics. So that's what we're going to look at now. So what's a linear bicategory? And this is due to Cockett, Kowslowski, and Seely. Linear bicategory is the bicategorical analog of an LDC, right? Essentially, you've got this class of zero cells. You've got a category with one cells and two cells and your domain codomain functors. And then you want a tensor bicategorical structure. So you have a tensor composition and these tensor units, tensor identity one cells, right? And then you've got a par bicategorical structure with a par composition and par identity one cells. And you want to satisfy your left and right linear distributivities. And the coherence conditions, are precisely the same ones as for LDCs, just, giving everything domain and codomains, right? Your objects become one cells and your maps become two cells. Okay, so some examples. Every bicategory is a linear bicategory. It's the degenerate situation where you take both compositions, your tensor and par to be equal. Of course, given an LDC, its suspension will be a linear bicategory. Okay, the most important example, rel. The locally post-settled bicategory of sets and relations is a linear bicategory. Your tensor composition is standard relational composition, and your par composition is sort of this relational sum. Your exists becomes a for all, and your and becomes an or. Okay. And then we'll see that they're related by De Morgan duality, actually. And then your identity one cells is the diagonal relation and the inequality relation. And it's pretty straightforward to show that your linear distributivities hold in these instances. Another example is you can sort of generalize rel by looking at what me and my co-authors called LD quantals, which is just a linearly distributive category that's a quantal and on the tensor side, and then an op quantal on the par side. But essentially, you get these two, this tensor composition and this par composition that generalize rel. Okay, because rel is just this, but with the truth value 0, 1 quantal. And this is a locally post-setup linear bicategory. And then another example that was given by Cockett, Kowslowski, and Seely is if you start with an LDC that has linear products and coproducts, which they define, then you can take the matrix bicategory of natural numbers and then matrices and then families of maps between them. And then you can give a tensor composition, matrix composition, and a par matrix composition based on the tensor and the par in the original LDC. And this will be a linear bicategory. Okay, so let's talk about, because this is a linear bicategory. So in a sense, this is the bicategorical semantics for multiplicative linear logic. If you've removed the exchange rule, you've removed linear negation, right? So here you've got a really minimal logic. But we want to talk about, having negation. So how do we do that? Well, we talk about adjoints. So this is sort of the linearly distributive notion of adjunction in a bicategory. So a linear adjunction, right, is a one cell, which is the left linear adjoint from X to Y, and a right linear adjoint from Y to X, so R and S. And then you have a unit and co-unit, two cells, which are precisely the unit and co-unit from normal adjunctions, except that you have to be careful about par and tensor, right? So tau goes from this is your co-evaluation or your unit, goes from 1x to R par S, and then gamma goes from S tensor R to bottom Y, and then you follow these snake equations. You want to satisfy these snake equations, which are the same snake equations or the Yankee equations or whatever, but you have to add in that linear distributivity since you're going from two different versions of composition, right? And you should recognize these because it's precisely the complementation pair, but bicategorical. So this is one of the instances where the non-commutative semantics really shine in the bicategorical variant, I guess, because complementation pairs suddenly have a very explicit like way to look at them through this adjunctions, which are very natural in the bicategorical sense. So essentially, given an LDC, if you look at a complementation pair, it's going to be a linear adjunction in the suspension. Okay. One thing to note, and this is just unfortunate, you know, notational conflict, is that left linear adjoints model right linear negation and right linear adjoints model left linear negation, which is unfortunate, but that's the way it is. And so we can say that a linear bicategory has negation if there's a way to assign a left and a right linear adjoint to every one cell. Okay, so you get a right perp and a left perp that assigns. So given a one cell, you will have this left linear adjoint, which is the right negation, and then a right linear adjoint, which is the left negation. And then, of course, the suspension of an LDC with negation is a linear bicategory with negation. All right. Well, what about defining things in terms of closure? Well, we can do that. We just have to look at what closure is in bicategories. Just going to take a second to, flash the definition of what it means to be closed in bicategories because it's perhaps slightly less well known than closure in monoidal categories. And there seems to be a few different terms. So I'm citing Street here, but in fact, he uses right lifting and right extensions, where I'm using right HOMs and left HOMs because that's what Cockett, Kowslowski, and Seely use. But it's the bicategorical analog of closure. So a right HOM from R, which goes from XY to S, XZ, you just have to be careful about domains and codomains, right? It's a one cell R implies S from Y to Z with this this evaluation two cell that gives you this universal property, right? That you can take any two cell R tensor T to S and get the curry, which is T. Oh, there should be a double arrow there to R implies S, right? And equivalently, you have the following natural isomorphism, okay? Which should be recognizable. Again, you just are careful about domains and codomains for your one cells. And then dually for left HOMs. Now, in a linear bicategory, you can have right HOMs and left HOMs, but you want to consider them to be linear. So a right HOM is said to be linear if it's absolute with respect to par. What does it mean to be absolute? Which is something that existed, being absolute with respect to something in terms of closure in bicategories was already, a defined thing. But we say that it's absolute if R implies S parring with T is itself the right HOM from R implies S par T. And on the next slide, there's going to be perhaps a more indicative explanation for being absolute. But we say that a closed linear bicategory is a linear bicategory with all these chosen right and left linear HOMs. Okay? All right. But what does it really mean to be a linear HOM? Well, we say that we can, prove, that the right HOM is, R implies S, is linear, or, let me backtrack. If we have a right HOM, R implies S, then R implies S par T is a right HOM as well, precisely if this canonical two cell is invertible. So in other words, the right HOM R implies S is linear if this canonical map is always invertible for T. What does this say? Well, this is precisely the Grecian laws. So being a linear right HOM or a left linear HOM is just saying I'm a HOM, a right or left HOM, that satisfies these Grecian laws. So this is another instance where the bicategorical aspect brings a lot of sort of intuition to the stuff that we had in the LDC case, right? So instead of just saying, hey, we want these laws to hold, in the Grecian LDC, we're saying, no, we want to have closure that's absolute with respect to our other composition. And so, of course, a Grecian LDC, its suspension will be a closed linear bicategory in the sense that we have all chosen left and right linear HOMs. Yes. And so altogether, that gives us the bicategorical semantics for multiplicative bilinear logic. You got linear bicategories with negation and closed linear bicategories. And I've given the just a sketch of the proof here, but it's what you expect from when we looked at bilinear logic. It's the same thing as was happening in the LDC case. And note the star autonomous bicategory, right, doesn't appear in the literature, but it's alluded to many times, and it should be fairly, it's fairly straightforward to write. It's just the bicategorical analog of the non-symmetric star autonomous category as defined by Barr. Okay, so look at some examples. Well, rel, right? Its linear negation is the complement opposite or complement transpose. So our perp is all the y x's such that xy is not in R. And then if we look at QREL, that has negation if your quantile initially had negation. So it's a Girard quantile and as defined by Yetter. And an easy example of that are all Boolean algebras. So those are your Girard quantiles that are locales, in fact. And then your Q relation, the linear negation of that, will just be point wisely defined as the linear negation of all, in Q, right? So on the left-hand side here, I'm talking about linear negation in QREL. On the right-hand side, it's the linear negation as defined in Q. And then you can do the same thing for the linear bicategory of matrices. If you started with a star autonomous category or, an LDC with negation, then you can, of course, define negation in your matrices. Now, examples 2 and 3, you can define distinct notions of linear negation if you started with a Q or an X that had distinct notions of linear negation, right? But the thing is that most natural examples are either of star autonomous categories are either symmetric or cyclic, right? As we previously discussed. So it makes sense to look at cyclic linear logic again and look at the bicategorical semantics for that. So Kozlowski introduced the bicategorical analog of the cyclic star autonomous category in 2001, which was the same time linear bicategories were introduced. So all of this sort of, they all had the same idea at once, right? And it was really to look at a bicategorical cyclic tree construction. And the cyclic star autonomous bicategory is a bicategory where you have these local linear negation functors, the star. So for every pair of zero cells part of X and Y, you have this adjoint equivalence. And what we're seeing here, if you look back at the non-symmetric star autonomous category, you had this equivalence, right? But here you're saying, I want it to be a self-adjoint equivalence, right? You want your left star to be actually the right star op. And that's what enforces it to be cyclic, for there to be one version of linear negation. And then 2 says that, in fact, R star should be the right HOM from R to the identity star. And for this to all be natural in R. But the second thing is sort of a minimalistic way of writing these natural isomorphisms that, we've seen in the star autonomous case. So this is sort of to be expected definition. And, we should be able to reformulate this in terms of implication, right? And the cyclic dualizing one cells. And that's precisely what you can do. So the only difference here is instead of having one cyclic dualizing object, you've got a family of them, right? So you need a family of one cells in a closed bicategory. And you say that this family is dualizing if the canonical 2 cells, which you get from right currying the evaluation, left currying the evaluation, and then right currying the co-evaluation, are invertible. And you're cyclic if you have, all right, these invertible 2 cells, which essentially say, okay, right negation is isomorphic to left negation. And then you say you're cyclic star autonomous bicategory if you're closed bicategory with a cyclic dualizing family. Um, Now, Cockett, Kowslowski, and Seely also developed the notion of star linear bicategories. And this is the idea of linear bicategories with one notion of negation. So you can think about it as a closed linear bicategory where you have this natural isomorphism satisfying coherence conditions, or equivalently, there's this idea of these cyclic linear adjoints. I won't get into it for time's sake because unlike cyclic star autonomous bicategories let me go backwards, where you only have sort of one coherence condition for this isomorphism here, in the linear bicategory case, you have many, like quite a few more diagrams because you have to interact with Barr as well. And then cyclic linear adjoints, actually, it does, get fairly involved to describe. So, well, not the cyclic linear adjoint point, but what happens with the two cells. So for time's sake, I won't describe it, but altogether, you get the bicategorical semantics for multiplicative cyclic linear logic, which will be your cyclic star autonomous bicategories in terms of negation or implication, and your star linear bicategories in terms of negation or implication. And that's all I have to say. Here are all my references. But yeah, it's just been an interesting sort of literature review and digging into all these different variants of the semantics for these variants of non-commutative multiplicative linear logic, and actually seeing how the bicategory aspect brings a lot of clarity to what was going on in the categorical aspect. But that's it. Thank you.
Thank you very much, Rose. Are there any questions? Okay, if not, I have a question about something you said at the very beginning,
Yeah.
saying that this is the bicategorical version of only the multiplicative fragment of linear logic. But now if we want to look at full linear logic, I assume for the additives, it corresponds at the bicategorical level to have the local home categories, to have products and coproducts. But do you have any intuition on the exponentials and how it would look like on the examples of REL and profunctors?
The direct answer is no, I don't, because this isn't at all developed yet. Like they developed what linear functors are for linear bicategories, which were developed in LDCs to talk about the exponentials and the additives, but they didn't pursue that at all. So this is precisely a project that I think would be interesting, is looking at exactly what the exponentials would look like, and on REL and everything, what that looks like in the linear bicategorical setting.
Okay, thank you. Any other comments or questions? Okay, then let's thank Rose again. Thank you very much, Rose.